Number 9 is about the same problem that was in the video. Deal with carbon monoxide attaching to hemoglobin. Normally, hemoglobin makes oxyhemoglobin, but in this case, it makes carboxyhemoglobin, which is really, really bad. You wouldn't be able to carry oxygen to your cells in the body if your red blood cells were saturated with carboxyhemoglobin. Anyway, this equilibrium is an equilibrium between oxyhemoglobin and carbon monoxide, making carboxyhemoglobin and oxygen. Um, they're all gases or aqueous, so they all actually participate in the equilibrium expression. The equilibrium expression of this reaction is K equals the carboxyhemoglobin, which is the product here, times oxygen. I'm using parentheses because the oxygen is in the gas phase, so we're going to use atmospheres for that instead of molarity, over the oxyhemoglobin, which is the reactant, times the carbon monoxide, which is also the reactant. Right? That's the K. Now, I didn't make a rice table here because we're not actually going to need it. The question is what partial pressure of CO in the air is likely to be fatal. The deal is it already gives you enough information to solve this without actually making an ice table because it tells us that this fraction right here is equal to 1. So that will reduce to 1. Right? It also tells us that the oxygen is 0.20 atmospheres. And it tells us that the K is 2.0 times 10 to the 2. All right, if you came here looking for hints, try to solve it yourself from this point forward. You don't need the rice table. All right, once I plug all that in, I get 2.0 times 10 to the 2 equals, we know that that reduced to 1, 0.20 over the concentration of CO. So we're trying to solve for the amount of CO. All right, we know that 1 doesn't really matter here. So when we try to solve this for CO, we're going to get the amount of CO is equal to 0.20 over 2.0 times 10 to the 2. And so therefore, the amount of CO is equal to 1.0 times 10 to the negative 3 atmospheres. All right. So that is the amount of CO. It's a really tiny amount. We see that it's a really tiny amount because K is so large. In other words, K really favors the products here. You're going to get a lot more products than reactants. All right. We can also assume that the other part of the question, why is this assumption valid? The amount of oxygen in the air is about 20%, and atmospheric pressure is 1 atmosphere. So about 20% of 1 atmosphere is the partial pressure of oxygen in the air, which is 0.20. That's a reasonable assumption. It's actually about 21%, not too far off. All right, for B, we're going to use the trick that we know. If you want the reverse reaction, you take the reciprocal of K. So 1 over K is going to be the K of the reverse reaction. So all I'm going to do is I'm going to take the reciprocal of K, which we already know that K is 2.0 times 10 to the positive 2. So the reciprocal of that is going to equal our new K. And so when we do that out, we're going to get the K of the reverse reaction is 5.0